Okay. So good afternoon, everyone. My name is Pavel Sukhachov. So today I would like to talk about some recent research done together with Leonid Glassman at Yale University. But before we start, okay, I can introduce myself a little bit. I got my PhD from Bogolubov Institute for Theoretical Physics, where I worked with Professor Eduard Korbor, on Dirac and Weyl semimetals. After that, I moved to Western University, where I worked with Professor Miransky, Vladimir Adolfovich, where we continued to work on physics of Dirac and Weyl materials. Then I did my second postdoc together with Professor Balatsky, where we worked on various aspects of unconventional superconductivity. And then I moved to Yale, where I got Yale Prize Fellowship, and where I am actually now. So there we also work on different aspects of topological materials and superconductivity with Leonid Glassman. So to start with, let me probably introduce what are these Dirac and Weyl materials, which I was interested that much. So as the name suggests, Dirac and Weyl relativistic equations play an important role in describing physics of Dirac and Weyl materials. Indeed, if we draw a cartoonish description of just a second. Now it's better. Of the low energy spectrum, we will see that it contains a number of so-called Dirac or Weyl nodes, as you can see here, for example. In the vicinity of these nodes, the energy spectrum is linear. It's quite unusual because usually we think that it should be quadratic in conventional solids, but here it's linear. As such, nontrivial dispersion attracted a lot of attention both from experiments and from theory. Indeed, in 2014, Dirac semimetals were experimentally discovered in such materials as trisodium bismuthide, cadmium arsenic 2 compound, and a bit later in zirconium pentatelluride. Well, there is another material which is bismuth antimony alloy, which can also show three-dimensional Dirac spectrum, but it requires fine-tuning of its composition. So as you can see, for example, from this cartoon, from this data, this experimental data, made by using ARPES, which is angle-resolved photoemission spectroscopy. The spectrum is indeed linear, but the Dirac node is quite below the Fermi surface here. So it's here. In the case of Weyl semimetals, we could have two Weyl nodes, and I will briefly explain why this is the case just in a few minutes. And the energy spectrum was also mapped by using angle-resolved photoemission spectroscopy, as we can see here, for example. Experimental data for such material as tantal arsenic, which is a member of a larger family of materials known as transition metal monopeptides. Later, other materials, such as, for example, this cobalt stannum sulfur compound and the European cadmium arsenic 2 compounds, were experimentally discovered to be also Weyl semimetals. Any questions? Okay. So these materials, unlike previous ones, they are magnetic. So these are non-magnetic and these are magnetic, and this would play a certain important role in what I will be discussing. We have experimental data. We know that these materials exist. Now we need a theory to describe their properties. Perhaps the simplest model to describe a single Dirac node would look as follows. So we have a 4x4 Hamiltonian. Here, sigma is a vector of Pauli matrices on pseudo-sphere space, I would say. And so why 4x4? Well, we have two bands, okay? This gives us 2. And then we have spin degree of freedom, so another 2, so 2x2. So it's possible to arrange the corresponding low energy spectrum in the same form as it appears for low energy for Dirac fermions in high energy physics. However, here we don't have mass on the off-diagonal, and we have replaced speed of light with Fermi velocity. The energy spectrum of such Hamiltonian is very simple. It's just a single Dirac node. It preserves both inversion, parity inversion symmetry, and time reversal symmetries. The node is doubly degenerate. Well, one might say that, well, in Dirac metals, this bands can hybridize and open the gap, but this doesn't happen because there is some crystal symmetry usually that protects these nodes from hybridization. In the case of Weyl metals, we need to separate these Weyl nodes either in momentum or in energy space. Here, for example, by breaking time reversal symmetry, we can separate the Weyl nodes in momentum space, as one can see here, or in principle, we can separate them in energy too. The corresponding separation parameter is called chiral shift parameter. Unlike Dirac metals, in the case of Weyl metals, the Weyl nodes are protected by topology, which means that each of the nodes is a monopole, so-called Barter curvature. I will introduce this quantity just in a minute. And it has a non-zero topological charge. This fact means that we can just remove a single Weyl node because topological charge is also conserved in such a system. And we can remove and create Weyl nodes only in pairs of opposite topological charges, which in the case of Weyl metal is usually referred to as a chirality, which just essentially is a sign here in front of these lower and upper blocks. So what is this Barter curvature and where is this nontrivial topology in Weyl metals? To start with, I will follow generic arguments introduced by Sir Michael Berry. His seminal paper written quite a few years ago. So we consider a adiabatic evolution of the system, which means that during the evolution, the system remains in its instantaneous eigenstate, some phi n, with energy dispersion relation epsilon. Then, if we have a closed trajectory in the parameter space, the wave function will acquire additional phase if there is a nontrivial topology of the space. Well, of course, there is a conventional phase related to the just dynamical evolution, but we are not interested in that. But this phase can be removed. And it's actually physically observable. It's manifested in several experiments, such as quantum oscillations, for example. Such a phase can be rewritten in terms of the so-called Barry connection. Indeed, it's a loop integral in the momentum space over a Barry connection, which is written as follows. Therefore, we are at the conclusion that the nontrivial topology of Weyl metals is essentially hidden in the structure of their wave functions. And such non-triviality is not possible for conventional materials that are not described by multi-component, for example, spinors. This Barter connection, if one takes a look, it's non-gauge invariant, which means that one can add a full derivative to this quantity. And therefore, it's somewhat reminiscent to the vector field in electromagnetic, in the case of Maxwell equations, for example, whereas the vector field is also non-gauge invariant. By using this analogy, we can introduce a gauge invariant quantity, which is known as a Barter curvature. We can see here. Barter curvature will be the curl of this Barter connection. It's completely observable gauge invariant quantity. And in the case of simple Weyl metal with two Weyl nodes, it looks as follows. So Weyl nodes here are either sources or sinks of the Barter curvature. The total flux through the whole brilliant zone, this box, is conserved, just essentially like an electric charge dipole. Essentially, this leads us to conclude that since the total flux through the whole brilliant zone is conserved, it's actually zero because such spheres that surround the whole brilliant zone is equivalent to just a point in the middle of the brilliant zone. And of course, if we just remove a single charge, we will create a zero flux, and we're just breaking this law of topological charge conservation. What's the lesson? Our Weyl metals have a nontrivial topology quantified, for example, by the Barter curvature. And this Barter curvature is reminiscent to a magnetic field, but which acts in momentum space rather than in real space. Such analogy suggests Yeah, is there any questions? Because I constantly hear that there is some. Okay, there's some background noise. The point is that the Barter curvature is very similar to a magnetic field, but in a momentum space. This suggests that while some metals might have nontrivial properties subject to a magnetic field. What do we know about magnetic fields? If you take a look at the transport in magnetic field, well, if magnetic field is parallel to electric current, we don't expect anything interesting to happen because there is no Lorentz force in this case. But of course, if it is perpendicular to applied current, there will be Lorentz force, and usually it increases orbits of electrons, and hence it leads to an increase of the resistivity. Or because our electrons can encounter more impurities as a without magnetic field. But even if we do have a material with a non-spherical Fermi surface, then there is some dependence on a magnetic field, which is along the current. But usually, again, the resistivity grows with magnetic field. And this would be a conventional picture for a magnetic field in usual metals, such as gold, for example. However, as was shown in Weyl metals, situation is a little bit different. For certain fields, as we can see here, for example.
And what is this picture on the left? It's not clear.
This picture.
Yeah.
This is the angular dependence of the resistivity on a magnetic field. So we have say current running in one direction, and then we can just rotate magnetic field.
For which compound? For which compound? It is so strong. I never.
It's gold, actually.
Just for gold.
Right. Well, one could take a look at conventional textbooks like Abrikosov, Kharkov, for which I took this picture. But yes, if the Fermi surface is unusual, then the dependence might be rather strong. And of course, here it's probably normalized. That's why it looks that drastic.
But why not symmetric? It should be symmetric at least.
Well, ideally, perhaps yes, but why it's not symmetric in this case, I don't know. Actually, if one takes a look, there is some symmetry here. Well, for example, this slope is very similar to this slope. This slope is very similar to the slope. Those probably
should be the symmetry of the Fermi surface at least.
Right, but as I'm saying, there is a symmetry of this plot, but not with respect to zero. It's, for example, with respect to this axis.
Maybe if there is no inversion symmetry. Do you have inversion symmetry in this material?
In gold? Well, I suspect that there is some symmetry there. But honestly, I don't know how exactly the Fermi surface looks like, so one should take a look.
In gold, you have inversion symmetry.
Yes, you should have, but I just don't have Fermi surface to show you. I'm sorry for this. So, but yeah, well, my point here is that there is some symmetry in this plot. It's just not about the zero axis. That's it. So it's actually about this axis. If one takes a look here, that one can clearly see that there is inversion symmetry. Then, does this answer your question?
Okay. Just continue. Sorry.
Okay. But well, this is actually not important for our discussion. The point was just that usually we have an increase of the resistivity with magnetic field. But in Weyl metals, on the other hand, if you take a look at the dependence on the magnetic field, the resistivity can actually decrease with the magnetic field. As one can see here, there is a region where the resistivity clearly decreases. And such decrease is usually known as a negative magnetic resistivity in Weyl metals. It's quite an unusual phenomenon, and physicists were excited to link it to the so-called chiral anomaly. Chiral anomaly, this term comes from high energy physics, and there it's a very important phenomenon that describes, for example, that's important for the description of the decay of neutral pion into two gamma quants. It appears due to nontrivial regularization of triangular diagrams, and it essentially states that in the presence of electric and magnetic field here, the so-called chiral or axial or imbalance current is not conserved. This chiral current, which essentially is a current which is a difference between, let's say, particles of positive chirality and negative chirality. In our case, this would mean that there is a difference between the populations of right-handed nodes, let's say nodes with a positive topological charge, and left-handed nodes. And well, actually, there is a much simpler way to understand the appearance of the chiral anomaly without invoking any triangular diagrams and regularizations. For this, we can just recall the energy spectrum in the magnetic field. So if we apply magnetic field to a Weyl semimetal, we will arrange its energy spectrum in the set of Landau levels. And the lowest Landau level in Weyl semimetals is very unusual. It's chiral. So this means that there is a linear dependence on energy, linear dependence between energy and momentum here. So, and the slope is different for Weyl nodes of opposite chiralities. So here is, for example, negative. Here is, for example, positive. Now let's apply magnetic field. Sorry, electric field. What will electric field do? It changes momentum of our electron quasiparticles. But the change of momentum due to this linear dispersion relation is directly linked to the change of energy. Therefore, by applying electric field, we will change the population of this lowest Landau level. We will increase its population here and decrease it here. And if we just take a look at a single Weyl node, we will see that something anomalous happens. The charge starts to just appear out of nothing, and we are now pumping this right-handed charge. But in fact, in real source, these Landau levels are always connected somewhere deep below the Fermi surface. And hence, we are not just creating charge out of nothing. We are just redistributing it from, let's say, left-handed node to right-handed node. And hence, we're creating this imbalanced population, which essentially leads to chiral, which essentially is chiral anomaly. Okay, but why it is important for transport and how can it lead to negative magnetic resistivity? For this, we can consider the propagation of a wave packet in a Weyl semimetal. We can say that this wave packet is charged, so it has a non-zero electric charge, but say it composed of equal amount of right and left-handed Weyl fermions. So its populations of the left and right-handed nodes are the same. Then, if we don't have any magnetic field, we don't have a chiral anomaly, and this wave packet will just spread due to interaction with impurities, for example. So this broadening is just a conventional broadening. But now what happens if we apply this magnetic field? Well, in regular materials, nothing drastic, but in Weyl materials, due to this structure of the energy spectrum, we already see that, first of all, there are more left-handed particles here than here. Indeed, there is an imbalance in the velocity of right and left-handed Weyl nodes. So this fact number one, which is related to the presence of magnetic field. Second is, of course, that there will be chiral anomalies that will redistribute populations of right and left-handed nodes. Therefore, our wave packets will start to separate in coordinate space due to this imbalance of velocities, and the populations will become different because of the chiral anomaly. And what do we have here? We have electric charges, indeed, these charges are still electric, that are moving in opposite directions in coordinate space, and this is nothing else as an electric current. So we arrived to the conclusion that the presence of magnetic field leads to the additional anomalous component of the velocity, which is manifested in the additional electric current. Hence, it modifies the conductivity, and the modification is positive here. So we have this negative magnetic resistivity. So magnetic field essentially helps material to conduct current. Well, great news. We have chiral anomaly discovered in solids. But in fact, as usually happens, there are many other effects that can mimic such a chiral anomaly. For example, one of them is a so-called current jetting. This phenomenon appears because of the non-trivial electric current distribution in the materials, with large anisotropy in their resistivity. For example, if we consider a homogeneous material with without any anisotropy, then if we apply point contacts here, the distribution of electric field will be more or less homogeneous inside material, and we can measure it both inside material somehow, or maybe as a side surface, it will be sufficient. But if our material has a large mobility and we apply magnetic field, we will create a large anisotropy. And this large anisotropy will lead to this current jets that are created out of point contacts. And then if we try to measure our voltage drop at side surface, we will see that there is a huge voltage drop if we apply magnetic field. But this voltage drop appears not because of the Chiral anomaly, but just because of the redistribution of the electric current. And early experiments on Weyl emitters were actually plagued by were subject to this problem, and some of them should be actually revised. Nevertheless, some techniques were improved. And we still can claim that we can measure Chiral anomaly in DC transport experiments, but such a deficiency prompted us to develop a new technique and probably develop a new experiment to investigate the manifestations of the Chiral anomaly. And for example, with Leonid, we proposed to look for the Chiral anomaly effects in the sound attenuation experiments. So what do we know about sound attenuation? If we deform a lattice, of course, electrons will follow, and if there are any excitations on top of the Fermi surface, these excitations eventually will lead to the dissipation of our sound energy. So mathematically, strains can couple to the electron dynamics with so-called deformation potential, which looks as follows. The following term is a Hamiltonian, and where UIG is just a symmetrized strain tensor. So the simplest deformation potential will be just a constant here, which will change the Fermi surface as follows. Looks nice, simple, but in metals, this doesn't work, because if we change the volume of the Fermi surface, we are breaking local charge neutrality. But in metals, there is a strong screening, and this breakdown and deviation of the local charge neutrality are quite costly in energy. Hence, such channel will become suppressed. What will happen there is that we can deform Fermi surface. So excitations will look as follows. They preserve the volume of the Fermi surface, and the corresponding deformation potential is just momentum dependent. In our Weyl materials, or in principle any other multi-valley material, so where there are several valleys, we can have deformation potential that depends on this valley. So we can increase the volume of one Fermi surface and decrease the volume of the other Fermi surface. And while this preserves the total Fermi surface volume, there are changes. And I argue that this would be the main sound attenuation channel in multi-valley materials. What will happen then? If there is no magnetic field, then Weyl materials are no different from conventional multi-valley materials. Here, if it creates, for example, a wave packet with equal in magnitude but opposite in charge populations of right and left-handed fermions, Weyl fermions, well, this wave packet will just spread if there is no magnetic field. But if we include magnetic field, then something different will happen in Weyl metals. So in conventional materials, the difference will be probably negligible in the case of semi-classically weak magnetic fields, and if the Fermi surface is spherical. But in Weyl metals, as we discussed before, there is a difference between right and left-handed nodes in the magnetic field. There is this additional velocity difference here. And hence, this wave packet, which is composed of right and left-handed Weyl quasiparticles, will start to separate in coordinate space, as you can see here. Before electric charge neutrality was locally preserved. So this positive and negative charges exactly compensated each other, and we were working in this picture essentially. But now, if we include magnetic field, we will force wave packet to become separated in coordinate space. Hence, there will be regions where the local charge neutrality is broken. So this means that, well, by including magnetic field and activating the Chiral anomaly, we are breaking local charge neutrality, and hence we will invoke the Gauss law, and hence we are moving from this picture to this picture. So we're after the conclusion that the Chiral anomaly actually leads to the decrease of the sound attenuation because it blocks one of the sound attenuation channels. Well, this is rather hand-waving arguments, and how essentially we calculated, how we arrived to this conclusion. Here I'm switching gears a little bit and going to more technical details. So what is the sound attenuation coefficient? Essentially, this is just dissipated energy divided by a volume of the system and divided by the sound energy flux. Dissipated energy can be calculated as averaged over the ensemble time derivative of Hamilton. And we also should average it over the period of our sound wave. A sound energy flux is just a simple expression that is valid for any material. There is no wildness here. So essentially, it depends on the speed of sound and mass density of material. But let's focus on this part. Actually, we've usually people calculate sound attenuation via entropy production, but we found it more convenient to rewrite it by using this expression for the dissipated energy. The benefit is very simple, because the only part of Hamiltonian that depends on time is the deformation potential. Actually, we need only to calculate the correction to the distribution function up to the first order in deformation potential, or rather to the second order, as usually done for the entropy production. Indeed, well, since we do have this averaging over the period, we need to have we need to essentially go to the second order in order to get a non-zero result. So by using this expression, we arrive to the following result for the sound attenuation coefficient. So here it is important just to emphasize that sound attenuation coefficient is proportional to the deformation potential and the deviation of the distribution function caused by this potential. This option. So we assume that the deformation potential is known in our case, so just given us. So the only thing that we need to essentially calculate is this correction to the distribution function. So essentially how electrons are perturbed by this deformation potential. And we did this by applying kinetic equations in the diffusive approximation. Well, here's a kinetic equation. It's rather long, so let me maybe go through it in details. So these first two terms are essentially just a regular continuity equation for a single Weyl node denoted by alpha. This part is the anomalous term, which is related to the Chiral anomaly. So essentially, it's just E dot P term, which says us that the chiral charge is not conserved. The electric field here is composed of two parts. It's dynamical electric field induced by exactly this breakdowns of the local charge neutrality, and additional component of the electric field related to the deformation potential, because essentially deformation potential shifts energy, hence it will create additional electric field. There are also terms on the right-hand side which are related to the inter and intra-valley scattering. So here is inter-valley energy transfer induced by deformations. And this part is essentially inter-node scattering. So everything is here. Well, in each of the nodes, the electric current, or maybe not electric current, but just current, reads as follows. So it contains two familiar terms, which is a diffusion term, which is an ohmic term here. Well, this term is also part of the ohmic term because this is an effective electric field. And also what is important for us, there is an anomalous part of the current, which is exactly related to this velocity imbalance that we were talking about before. It's proportional to this anomalous velocity, and of course, it's proportional to the deviations from the equilibrium value of nodal charge. And another important law that was actually omitted before is a Gauss law, which defines the relation between this induced electric field and total charge deviations. And this is actually, without this law, we will not get the reduction of the sound attenuation coefficient. So now we have a well-defined problem. We have a system of equations. We can solve it. Well, it's pretty arduous, so I will skip the exact solution and we'll just focus on the results and their physical meaning. So without any magnetic field, we can obtain the sound attenuation coefficient, which is just the same as for any multi-valley conductor. And it agrees actually with the old results from Soviet literature from 1970s, 1960s. So here the sound attenuation is proportional to the deformation potential and frequency essentially of the sound. And there is also dependence, of course, on the diffusion and the internal scattering hidden in this tau cube. But now if we apply a magnetic field and consider Weyl semimetals, there will be additional correction related to this term, this anomalous component of the current, and it will go into the denominator. Hence, the larger the magnetic field, the smaller the sound attenuation coefficient. We can actually estimate it for more or less realistic parameters taken for tantal arsenic. And we can see that even for semi-classically weak magnetic fields, this white region, we can have the reduction of the sound attenuation up to 10, 20%. So effects should be quite noticeable, actually. Just we're not talking about 1 or 2%. We can a little bit stretch our results to the regime of stronger magnetic fields, not quantizing, but quantizing will be here, but still strong. These results should be still valid as long as the Fermi surfaces are spherical. So there, the reduction will be even stronger. What else can we say about our Dirac and Weyl semimetals? Actually, in Dirac and Weyl semimetals, their linear low energy spectrum can allow for quite unusual effect related to the possibility of strain-induced effective or axial gauge fields. Indeed, in addition to the deformation potential, by deforming the lattice, in this case of Weyl semimetals, we're also inducing actually vector parts of this field, vector parts of the, I would say, effective gauge field. So this would be just a zeros part, and this would be the vector part. This can be understood as follows. So we can just take a lattice model of a Weyl semimetal. We can change the hopping parameters. We can assume that the change is weak, for example, and then we can again rederive the effective model based on this deformed lattice. And we will see that in addition to this deformation potential, there are these vector components of the field that depend on the separation between Weyl nodes in a momentum space. So the main benefit of such a field is that, well, it resembles a conventional electromagnetic field. However, it couples to Weyl fermions of opposite chiralities with an opposite sign. So instead of electric sign, it feels the chirality of our nodes. So this means that if you, for example, somehow create these axial fields with a specific time coordinate dependence, then we will be able to create effective pseudomagnetic and pseudoelectric fields. So, for example, we can introduce pseudomagnetic field, which is a curl of this pseudoelectric field, and this pseudoelectric field, which is just a gradient and time derivative of corresponding components of this axial gauge field. So the bottom line here is that we can apply some static strain to a Weyl semimetal on top of the dynamic strain induced by sound. And this static strain can be interpreted in terms of effective fields, if a pseudomagnetic field B5 or pseudoelectric field E5. And this actually is important for sound attenuation. So if we apply this, for example, torsion to a wire of a Weyl semimetal, and then we'll run a sound wave across the wire, we will see that there is a sound attenuation dichroism, which means that the sound attenuation coefficient is different if we run a sound wave along or opposite to the pseudo-magnetic field. Well, essentially the same effect can appear if we just have some non-symmetric Weyl nodes, breaking symmetry between Weyl nodes, and hence there is this asymmetry in sound attenuation. Unlike the previous effect, which was a reduction of the sound attenuation coefficient, the sound attenuation dichroism is rather weak. It reaches just a few percent, for example, here in the peak value. But still, nevertheless, it would be a very interesting manifestation where several non-trivial components, non-trivial aspects of semimetal physics play a role and are manifested. So I'm slowly moving to the conclusion of this part one of my talk related to the sound attenuation. So here, the key message that I would like you to take home is that the chiral anomaly can actually reduce the sound attenuation in Weyl semimetals subject to magnetic fields. This is quite unusual because usually we expect that, well, if we increase the conductivity of Weyl semimetal, we have this negative magnetic resistivity phenomenon, then via Joule heating, we should actually increase the heating of material. But in fact, taking into account the screening and chiral anomaly together leads to the reduction of the sound attenuation, and this is quite unusual. Also, on the technical side, we developed an effective method of evaluating sound attenuation coefficient by relating it to the solution of the kinetic equation. And finally, we found that asymmetry between Weyl nodes induced, for example, by this pseudomagnetic field by static strains might lead to the sound attenuation dichroism. So details can be found in our paper, and actually the papers that appeared exactly at the same time by Pesin, Andreev, Island, and Tepe. Well, one might say that sound attenuation is quite exotic phenomenon, and not many groups are willing to do it. So what is of interest now is usually electromagnetic field responses, such as, for example, light penetration and propagation through Weyl semimetals or various reflection experiments. So we decided to take a look at perhaps similar phenomenon and ask the question: how the chiral anomaly can affect not the sound attenuation, but, for example, a light attenuation, electromagnetic field attenuation. And this part of my talk is motivated by recent experiments, relatively recent experiments by Peter Armitage, where they were able to study the essential optical conductivity, which is related to the transmission and reflection coefficients of a film of a Dirac semimetal subject to a magnetic field. So there, they were looking at a little bit different quantity, but the message was that depending on the relative orientation between the electric field, between the polarization of the initial light and the magnetic field, we can have a little bit different effects in the conductivity. For example, if our electric field is perpendicular to the magnetic one, then we have just a conventional decrease of the conductivity with the magnetic field. But if they are parallel, then the chiral anomaly kicks in and we have an increase of the conductivity here. Our question was actually much simpler. We know that in any metal, light cannot penetrate it easily. Usually metals are reflective. Physically, this means there is a so-called skin depth, a skin effect, which means that light can actually penetrate material, but the penetration depth is usually small. It's determined by the frequency of the light, of the electromagnetic radiation, and the conductivity of our material. So here's the skin depth. It's inversely proportional to the frequency and conductivity, and usually it's rather small for frequencies of our visible light, for example. Less than micrometers here. And so far, we are talking just about conventional skin effect for experts, whereas the mean-free path is much smaller than this skin depth. So we have the skin effect. It's well known. It can be found in any textbook, for example, Landau-Lifshitz. But what do we expect from Weyl semimetals? And what do we expect from chiral anomalies there? Well, naively, maybe nothing interesting. We include magnetic field. We are introducing this anomalous component of the conductivity here. So there will be additional anomalous component of the current. Naively, I would say that, well, we are just increasing the conductivity of this skin layer. So we should just reduce the skin depth, and this would be it. Nothing interesting, right? But actually, we found that one can have a quite interesting regime. And this regime is related to the non-local response of this Weyl semimetal. So what happens here? If our electromagnetic field tries to penetrate our Weyl semimetal, of course it attenuates and it will be mostly localized in the skin layer. If we apply an external magnetic field, we will create in this skin layer this chiral charge imbalance, which essentially is that valley charge imbalance created via the chiral anomaly. But as long as we're creating this chiral charge imbalance, so this charge can actually diffuse away from the skin layer. So, yeah, and if the diffusion is very effective, this charge can effectively move away from the skin layer. It can reach actually the other boundary of our slab, of our film, and there it can be transformed back into the electric current, and then it can actually enhance the penetration of electromagnetic radiation. So on the face, if we take a look at the phase diagram of our response, what can we see here? For small frequencies, we have this DC regime where our common intuition that can just shift the conductivity works very well. If the diffusion of this chiral charge is not so efficient, I will be using this coefficient psi, which is dimensionless coefficient defined as follows. Whereas if this coefficient psi is small, which means that the diffusion is small, well, then we are in the AC alternating current local regime. But still, this intuition works, and where perhaps this experiment performed by Peter Armitage was done. But we could actually have a novel regime, which we advocated in our work with Leonid, which is an alternating current non-local regime. And in this regime, there will be this anomalous transmission. So hand-waving argument here is follows. So we are transforming the energy of our electric field into the chiral charge. And now this chiral charge decouples somewhat from electromagnetic dynamics and can propagate quite far in our material. So we are introducing an additional channel of the electromagnetic field energy transfer through a film. And hence the enhancement may be possible. On the technical side, actually, yes, question? Okay. On the technical side, we actually use the same system of kinetic equations as we used for the sound and sound attenuation, and they're actually quite easier. Less components here. There's no deformation potential, so I will just skip description of this part. But since we do have an electromagnetic field, which is now no longer longitudinal, but transverse, we need to invoke Maxwell equations. And Maxwell equations will be coupled due to these anomalous terms to the chiral charge dynamics. So eventually this means that by exciting this electromagnetic field can excite the non-trivial distribution of chiral charge, and this chiral charge can be transformed back into the electromagnetic field. Since we do have a system of differential equations, we need to impose boundary conditions. Of course, there will be standard boundary conditions like a continuity of electromagnetic fields, but there will be also boundary conditions for this chiral charge. We might require a very fast chirality relaxation, an alpha equal to 0, or vanishing normal component of the chiral current density. which will be vanishing derivative. And again, we can solve the system almost exactly by performing the Fourier transform, or perturbatively, for example, by first looking for solution for a magnetic field without, but for example, we can assume that magnetic field is weak. Then we can find the electromagnetic field distribution. Then we can find the chiral charge distribution, feed it back into the Maxwell equation, and find the correction to the electromagnetic field. I will just show the results because I'm not sure that people are that interested in the technical details. So if we are in the local regime, where this parametric psi diffusion is small, then the anomalous correction due to the magnetic field, in case of also metals, will be regular. So it will just exponentially decay with the thickness of the film. If we have a thick film, for example, and we are in the regime where this nonlocality kicks in, psi is large, then the anomalous component of the electromagnetic field is also exponential, but the exponential exponent here is different. It contains component psi, which means that the exponent is much smaller than in this local regime. And of course, if it is exponent, then, well, smaller might mean a lot here. And we can also consider the regime of a thin film, where the essential chiral charge diffusion is very efficient, and we have in polynomial dependence on the thickness of the film. So graphically, what do we have? That if we are in the local regime, then chiral anomaly always suppresses the transmission of electromagnetic waves, just because it raises the conductivity. But if we go into non-local regime, there might be an enhancement of this relative field penetration. Well, it depends on the parameters. It might be not that large, but at least we have a qualitatively different effect. So instead of just the suppression, we might have an enhancement compared to the case where there is no magnetic field. Of course, if the film is rather thick, then we might take a look at the surface impedance rather than the reflection of the transmission through the film. Well, unfortunately, the effects are. Is that a question? Okay. Unfortunately, the effects here are not that drastic as for penetration of electromagnetic field. So just to remind, surface impedance is defined as electric field divided by the total electric current in the slab. So essentially, current density integrated by whole thickness of the slab, which is assumed semi-infinite here in this case. And here the main conclusion is that there is a correction to the surface impedance. Number one. And second, it depends on the boundary conditions. So if we suppress the chiral charge as a boundary, then the correction, anomalous correction, will be much smaller. But in general, what do we have for surface impedance? Magnetic field reduces its real part here. And also it reduces real part and might a little bit reduce the imaginary part too. So the effects are not that dramatic as they were for penetration. So since my time is probably running out, I would like to summarize the key conclusions of second part of my talk. First of all, we notice that the chiral anomaly may lead to a non-local current response in Weyl and Dirac semimetals, even under the conditions of the normal skin effect. This is quite important because sort of have anomalous skin effect, but it's not anomalous in the case it's regularly used in the literature. We still have mean free path that is much smaller than the skin depth. So now, because of a weaker decay of the anomalous component of the fields, it's very possible to reach this anomalous enhancement of electromagnetic field penetration depth in the non-local regime. Also, we found that in principle, this anomalous part is manifested in a little bit different scaling of penetrated field in with frequency. And perhaps for the details, one can take a look at our paper. And actually, after we published our paper, a few other papers appeared that also studied the manifestations of light propagation in Weyl submetals here. So with this, I would like to thank you for your attention and would be very happy to answer your questions.
Thank you, Pavel. Okay, then I will continue then let's say the talk is open for the questions then.
Okay, my question. So, in your calculation, as far as I understand, you suppose that your Weyl points are exactly on the Fermi level, or Fermi level exactly on the Weyl. What happens if these Fermi point, Weyl points are above or below the Fermi level? And how important is to have the Weyl points on the Fermi level?
Well, actually, I would say I'm not assuming that Weyl points are on the Fermi level. That's actually the one of the points of sound attenuation part. So yeah. So here this cartoon assumes that there is this level here, but by invoking this screening effects, I'm assuming that my Fermi level is actually quite above the Weyl points. So that's why I do have this large charge. That's why I have the screening. If we have Weyl points exactly as a Fermi level, then I would say that screening becomes less relevant for this Chiral anomaly, and this result would be modified. So just to reiterate, so this result assumed that Fermi level is rather far from Weyl nodes. So we have a Weyl, I would say, metal than a semimetal here.
Does it mean that you have somewhere you have the optimum where the effect the largest? How to estimate the optimum just to see the effect? Optimal.
It's a good question. So I would say that we cannot go very high in the Fermi level, because if we go very high, then we don't have any Weyl physics there, because spectrum will start to deform. How to see optimum? Well, probably it depends on the spectrum of Weyl submetal. So we should go a little bit higher just to have some background charge. And my understanding is that we don't need to have chemical potentials around hundreds of electron volts to invoke the screening. Screening will be already quite efficient in 3D Weyl submetals. So we can be maybe around 5 to 10 millielectron volts from Weyl nodes. That's actually I was using. Right, 20 millielectron volts here. If you go higher, yes, screening will become even more effective, but we are risking to deviate from Weyl nodes, and the definition of the chiral charge will become less prominent. So I don't have a very well-defined answer to this question, but I would say that it should be sufficiently high to have strong screening, to be in the regime where our Thomas Fermi wave factor is much larger than the sound wave factor, but we should be low enough to be able to still use Weyl spectrum. And this depends on the details of the Weyl spectrum. Sometimes it is rather linear, and then quickly merges. Sometimes it becomes non-linear quite quickly. It depends.
More questions? While people are thinking about questions, maybe I then have a few questions, just
Sure.
naive questions. Let's say, I think it was on slide 10, just about attenuation, about changing of the Fermi surface volume. I do not, so the naive question, when you are saying about Fermi surface volume, in which I mean how you measure it, in a sense that You say that if you change the crystal structure lattice parameter, you change the Fermi surface volume? Or?
Well, my statement is that if I'm running sound waves through my material, of course, I'm disturbing lattice. And then the statement is that, well, technically, the dynamical deformation of lattice is somehow manifested in the electron dynamics. And one can expand the corresponding correction to the Hamiltonian of electrons in terms of angular harmonics. And zero angular harmonic for this essentially leads to oscillating Fermi surface, which is essentially like a.
It is just more complicated. I just wanted just answer from simple consideration. In terms of if we change the size of the lattice, the size of the lattice constant, we change the size of the Brillouin zone.
Right.
We change, of course, the volume of the Fermi surface in, let's say, in momentum, if you measure it in momentum, but you do not change it if you measure it in terms of number of states.
Right,
So
number of states is conserved.
Number of states will be the same. So, but if number of states are not changing, then where the effect comes from, I do not understand. So you started to explain it now, right? But
well, number of states remains the same, but this is exactly probably the answer that principle we cannot have such perturbations that do change the number of electrons in our system, because if I'm changing the charge in the case of metal, of course I will invoke screening here, so there is no such effect here. What can we have? We can have essentially some sort of deformations that still preserve this number of states, but they're just redistributing there.
Yeah. Okay, and I wanted to ask about this tau 5. I think it was a picture on slide 7. Okay, here.
Well,
how to just for normal scattering, if you applied electric field and you have this change of population on the left and on the right. So this change of population will be proportional to electric field multiplied by tau.
By tau 5.
Yeah, no, by just normal tau. I mean, normal tau. This means just in simplest tau approximation in Boltzmann equation.
Which charge we're talking about? If it is a charge.
No, I mean just for normal metal.
Okay, just single.
Metal,
okay.
Just, so here, if you see how it changes on the right comparing to on the left, it will be in this horizontal scale. It will be electric field multiplied by tau. Yeah, the scattering time on the Fermi surface, on the Fermi level. And now tau 5, it is related with this scattering from left to the right on your.
Right. So unlike the single valley picture where you indeed have regular tau for single valley, here we have a scattering between Weyl nodes. So so this essentially is just separation of the collision integral in two parts. One part describes the scattering inside each node, this will be tau, and the other part describes scattering between Weyl nodes, and this will be tau 5. And this tau 5 exactly.
But can you show here and to say that this difference is proportional to tau 5 or not?
So my statement is that the imbalance between, let's say, right and left-handed node is determined by electric field, magnetic field, and tau 5. So just tau 5 multiplied by this parameter.
And what is exact formula?
This can be easily derived from this continuity relation. So essentially, we have this continuity relation. We should add something like 1 over tau 5 here, and then so essentially, I can try to dig out the exact formula, but n5 would be just tau 5 multiplied by E dot B plus some coefficient. Let me try to find.
E multiplied by B.
E multiplied by B
So it's
and multiplied by tau 5.
okay.
Not exactly what I wanted. Maybe I can try to. This actually follows this equation.
And that without just simple tau, you call a regular tau. It is just scattering of charge scattering, let's say.
All right. So scattering within the same Weyl node has nothing to do with this chiral imbalance.
The same band. Okay, and finally, on the slide 5, I just was wondering how you draw this picture. I mean, with errors. It is result of model. Yeah, it is result of modeling, or it is just.
It's actually quite simple. So we can take a look at the well. Let me take some lattice model. Just a second.
I mean, is it momentum space on the right?
Yes, it's momentum space. So essentially, one can take, if you see it, we can take a Hamiltonian, which looks, let's say, sigma perpendicular. So for this picture, we need a periodic Hamiltonian. Sigma x sine kx plus sigma y sine ky plus sigma z, something like say some constant m minus cosine kx minus cosine ky minus cosine kz. That's it. So then one can solve up to some coefficients, of course. So then one can find the spectrum of this Hamiltonian, just wave functions, and calculate the Barry curvature via this relation. That's it. And then in the space of kx, ky.
It's really analogous as electric field, just let's say field. Like okay, it's like electric field. It looks like electric field, right? But I mean analogous to as you just consider field potential and make this like in Maxwell equation, very analogous, right?
Right. That was actually the point, that this Barry connection, this A quantity, is very similar to the gauge potential, which is also that's why the same notations. So here you have almost the same analogy, and can also say that we have some dipoles of the Barry curvature, monopoles of the Barry curvature.
Okay, thank you. More questions? I see.
Okay. If I am doing the experiment, which materials do you propose to consider?
Well, technically, all Weyl metals such as tantal arsenic, for example, should work. Of course, they have a more complicated structure, but let's say I don't require any specific symmetry for a realization of, for example, sound attenuation and light penetration. For sound attenuation, perhaps the sound dichroism would require a break in time reversal symmetry, because if we want to create the pseudomagnetic field, we need to break time reversal symmetry in the material. So there probably these cobaltate compounds might work. For just measuring sound attenuation, any Weyl or Dirac material should work, I would say.
In the beginning, you showed tantalum arsenic. You have
yes.
32 Weyl points close to the Fermi surface. How does it change the results?
Okay, tantal arsenic. This one.
Yeah.
Well, yes. Sorry, could you repeat?
I remember 32 Weyl points close to the Fermi surface.
Right. Yeah, this of course will complicate the results because we'll be scattering between Weyl nodes. But there, as far as I can remember, some Weyl nodes are grouped together and some pairs of Weyl nodes are rather far away in the brilliant zone. So as long as we have these well-defined pairs, we can still use our theory. But even going beyond the theory, I would say that the main effect, which is a reduction of sound attenuation, should remain the same, even despite that we have a larger amount of Weyl nodes. Weyl nodes will just contribute additively. So there is no dependence on the relative orientation of nodes here. Of course, there might be some corrections related to the fact that we scatter not within the pairs but within different materials. But actually, our theory, if we apply it for a more generic case, yeah, here we have this T alpha beta, which accounts for internode and internode scattering time between different Weyl nodes without any assumptions whether they're close or not. Of course, when we are doing some analytical calculations, we made an assumption that there are well-defined pairs of Weyl nodes. But in general, well, there are equations where one can substitute and solve. And I don't see how the effect will be strongly affected by this, by the fact that there are many Weyl nodes around. There might be some numerical deviations, but at the end should be the same. So it is not crucial to have well-defined just a pair of nodes. And the same actually goes for light penetration, because there the light will create this chiral charge imbalance, which doesn't depend on the Weyl nodes. Of course, the details of calculations will be different, but the effects should again remain. Sound dichroism, as I said before, might be sensitive to the position of Weyl nodes, because there it essentially depends on the vector of time relativity breakdown vector. In total arsenic, you will not have it.
But this still, this tau 5 is much larger than regular tau, right?
Right. Usual, I would say, for estimates for tantal arsenic suggests that it is up to 100 times larger.
Why then you do see the effect or expect to see the effect, since the smallest, the much smaller tau will screen it? I mean,
well, so essentially, this much smaller tau will screen it. No, it will not screen it, because essentially much smaller tau will just say that the population inside each of the Weyl nodes will equilibrate much faster. It has also to do with the equilibration of different Weyl nodes. And actually, it's there was this discussion in earlier papers about the order of limits. So as long as you are not keeping tau infinitely small, then you should still have the effect.
But if you consider, if you compare, let's say, Weyl semimetal and just topological insulator with one Dirac, do you see the difference?
I think that I will, because in topological insulator, essentially, this Dirac lives on the surface. It's two-dimensional Dirac, right?
Yeah.
And the screening in 2 dimensions is much weaker than in 3D. So there I would say that, so here the screening is crucial, because essentially it is a screening that leads to, that suppresses this channel. So if the screening is weak, then I would say suppression might be still there, but the effect shouldn't be that drastic. It's actually an interesting question, what will happen in topological insulators. Naively, I would expect the effect to remain. But first of all, there is no chiral anomaly there. So sure what are we even talking about? But there might be some effect of other kind related to this. So, okay, just to clarify, if just two-dimensional topological, two-dimensional Dirac spectrum, there is no chiral anomaly, so this effect will not appear at all. So might be some other effect, which I don't know. Perhaps there is there is something else.
Yeah, I probably didn't understand what means chiral anomaly, because why there is no chiral anomaly in topological insulator? It is just clear chiral anomaly.
Well, this chiral anomaly requires it exists only in odd dimensions, odd spatial dimensions. It exists in 1D, it exists in 3D. It doesn't exist in 2D. The reason is that if you apply magnetic field, well, it's not clear where to apply magnetic field. So, for example, in 3D, if you apply it, there is a well-defined direction along magnetic field.
No,
so
I thought that on topological insulator, there are chiral anomaly without magnetic field on the surface.
Well, there is a chiral anomaly probably for one-dimensional states. So for one-dimensional states, there is a chiral anomaly, but it doesn't require any magnetic field. In 2D, I would say that no.
Okay. More questions?
I have a question.
Please.
Can you hear me? Can you hear me?
Yes.
So actually, my research field is about superconducting resonator. Like briefly speaking, like testing the magnetic penetrate dips on superconductor, but we only focus on superconductor because if the like semimetal or normal metal, the DC response is so high, then the AC response is so low. Okay, like there are a lot of dissipation of the energy, so we cannot test those semimetal. But in your way, you use an optical way to measure the magnetic penetrate dips, so you can find those AC response of the semimetal. Is that right?
Right. You can investigate response of semimetals, principal metals via electromagnetic field, and for example, experimental data for a film of Dirac semimetal. So they measure optical conductivity.
Because we use current way, like to just pop the sample, and always if it is semi-metal or it's no metal, the resistance is so high, and there are a lot. If you look at material, that's like there are real part and imagined part of the resist, like the impedance and like there are impedance, the inductance and resistance. But for normal metal, the resistance is so high, so we cannot get the imagined part, the inductance part. So in this case, you can avoid the resistance of the material. Is that right?
So should I understand the question correctly? Right, by using optical means, you can principally map out both real and imaginary parts of the conductivity to the best of my knowledge with relatively decent precision and accuracy. Of course, maybe it will be hard to do this if you just apply contacts and try to run AC current through a material. Then it's a different experiment. But if we're talking about optical responses, at least I know the data that is able to do to probe our optical responses very well.
Okay, thanks.
Okay, thank you, Pavlo. Do we have any more questions? Okay, then we will finish. Thank you, Pavlo, once more.
Thank you very much for your questions and attention.
Thank you all for participation. Bye-bye.
Bye.